Good morning, Sydney.
Good morning.
And welcome to NDC Sydney 2018. My name is Beattie, and I'm going to open the conference today by talking to you about apps, algorithms, and abstractions. This is me. I am CTO at a company in London called Skills Matter. I have been building websites since 1992. I'm so old I remember when webmasters walked the earth. I'm a Microsoft MVP. I run a user group in London. I'm on the internet. I am on Twitter. I didn't always look like this. I was born in Kenya in Africa in 1978. And shortly after I was born, my father wanted to send a picture of me to my grandparents who were living in the UK. So he took this photograph. This is me when I was a junior developer. And he took it using an old-fashioned film camera and took it to a pharmacy where they developed it. And he took that picture, he put it in an envelope, and he posted it. It took about probably 6 weeks end-to-end for this picture to make it from Kenya over to Oxfordshire in the United Kingdom. One photograph, 6 weeks. Anyone want to estimate the bandwidth of taking 6 weeks to send a single photo? We're not talking broadband here. We're talking, I think, nanobits worth of bandwidth. But here today, in 2018, things are a little different. Much. Enjoy the conference. I'll see you next year. Within my lifetime, we've gone from this to this. We've gone from 6 weeks to send one photograph to being able to send pictures to somebody on a moving train being such an everyday occurrence. You know, we all take that for granted. How many of you get that? Like, you know, your partner just sends you pictures of the cat or the kids or, you know, and it doesn't need to be a big deal. When I was a kid, if you had a baby, you'd send a picture around the world. If someone got married, if somebody graduated from university, it was important enough to send a picture around the world. And now we just do it because the cat's being kind of derpy, you know? And what I want to do today, somebody asked me a little while ago, they're like, how does it actually work? And I was like, I have no idea. I do not actually understand 99% of the things that make that experience possible. So I went away and I looked it up. And that's what I'm going to be talking to you about today. So you take your phone out, you get the little pinging noise, you take your phone out of your pocket, and you see this, 4 bars of signal, because we're addicted to signal, right, here in 2018. What does that thing actually mean? You know, how does a phone in your pocket talk to the rest of the world wirelessly? And you're like, well, obviously the answer is radio. And it is. Radio is pretty simple. Radio is one of those cool things we didn't invent, we just kind of discovered it. You take a piece of wire, and you put some electricity through it, and it emits electromagnetic radiation. I'm not going to tell you why this happens. That's just how our universe happens to be wired. But if you put another piece of wire on the other side of the room or on the other side of the country, you can get your electricity back out because it picks up these waves and it recreates the original signal. Now, this was the first of many, many game changers that we're going to talk about in this, because as soon as people discovered you could do this, they realized that we can encode sound as electricity, and then we can transmit electricity wirelessly through the air, and radio broadcasting was born. And suddenly, for the first time in history, you could actually talk to somebody who wasn't standing in the same room as you. We could broadcast news, we could broadcast music. We invented transistor radio receivers, which, anyone ever build one of those crystal radio kits, which has no battery? It literally takes energy straight out of the air and turns it into a kind of crackly signal that you can hear. So That basic principle has not really changed all that much since the invention of radio. But as you can appreciate, there is a hell of a difference between the handheld receiver on the left and the handheld receiver on the right in this picture. And in order to make modern cellular communication work, they had to solve 3 problems. First problem is the strength of a radio signal is directly proportional to how far you're sending it. If you have a certain amount of power, you can send a weak signal a really long way. You can send a shortwave radio signal literally around the planet with one transmitter. But you can't include a whole lot of information. You know when you're driving way out in the country and all you can get are AM radio stations? AM, long distance, small amount of power, the signal quality is not great. You get into the city, FM radio, sounds a lot better. They can do stereo. We need kind of FM plus. We need really, really high degree of signal, and the easiest way to do that is to move everything closer together, which means either you have to get everyone in a very small space, or you need to build a lot of transmitters. And this is what a cellular network is. Every one of these transmitters all over the Sydney area is covering a couple of kilometers of city blocks. So you're never that far away. In really dense areas like downtown, there's probably one of these every few hundred meters. So first of all, your phone is very close to the transmitters that it's talking to, so we can pack a lot of signal in for a certain amount of power. The second problem they had to solve, radio is a broadcast mechanism, but it only works in one direction. You can use it, picture it like a highway. You can send information in one direction, you can send information in the other direction. If you try to send in both directions at the same time, it doesn't work. So we started having to come up with mechanisms to do what's called duplexing, sending information in 2 directions at once. One of the earliest systems they came up with was a thing they call time division duplexing. It's basically like saying, imagine you've got this piece of road between 2 cities, and you make a rule. We don't want any more head-on collisions, so we're going to say that during the day you can go in one direction, and after dark, you can go in the other direction. And at dusk and dawn, nobody's allowed to drive anywhere. It's a pretty simple mechanism, right? And then, someone comes up with the bright idea. They're like, this duplexing thing is working pretty well, but actually it's kind of dumb having to wait until dusk before I can go home from work, What if we just do it on every hour? So in one half of the hour, you can go one direction, everything stops, go in the other direction. And then some bright spark goes, well, actually, in one direction, we just got, little cars going. The other direction, we got lots of heavy traffic. Why don't we change the length of the time windows? So they say, okay, well, we have a little window every hour where traffic goes one direction, and the rest of the hour, everything goes in the other direction. Now, take the hour and go minutes, seconds, milliseconds, microseconds. If you get this thing down to microsecond time slicing, this is how the 2G network works that's still in use in some parts of the US. And they actually changed the length of those windows. So if you're streaming Netflix on the train or over a cellular network, they'll tweak it so that you send one packet going, I'm still here, and then the rest of it is allocated to downstream bandwidth. You start sending a big file or attaching an email, they'll flip the window. So you have lots of upstream bandwidth. Now, this is a pretty good system, but it has all sorts of headaches to do with having to synchronize clocks and various things, and once you get into people moving through different cells and stuff, it's very complicated. So somebody came up with the genius idea, why don't we just build another freeway? We'll have 2 roads running in opposite directions. Look at this. And everyone went, yeah, we could probably do that. So what they're actually doing is you're running 2 separate radio conversations on 2 separate frequencies at the same time, and then somebody went, well, if we got 2 of them, maybe we could have more. So when your phone gives you those 4 little bars which say you've got a good, strong cellular signal, what it's actually doing is there are about 16 channels that are dedicated to your phone. How many people in here, just take your phone out, look at it right now, put your hand up if you've got a strong signal. Yep. That is pretty much everybody. So every single one of you has got 16 channels of radio spectrum for your personal use in this building. Think for 1 second about the hardware that's in the receiving tower up on the roof of this building that makes that possible. And we take it for granted. And when you only have 2 buzzer signals, you're like, stupid thing doesn't work. It's like, no. The miracle is temporarily just a little bit less than it normally is. But with these 16 channels, they can dedicate all of them for different things. It's like having a freeway for the emergency services, and another one for the post, and another one for ambulances, and one for driving on. We've got all these dedicated channels just to allow these cellular data experiences to work. So the other problem they had with radio is anybody can stick an antenna in the air and they can pick up the signal and they can listen to it. Who would be up for having their email broadcast to everyone in the Sydney Greater Business District? Because I know I wouldn't. So the next thing they did is we got all these 16 channels, now we need to encrypt the whole lot. using a very complicated cipher, which is a combination of the IMEI code in your phone, the code in your SIM card, the manufacturer, a whole bunch of contracts, rotating keys, and all this stuff happens without us really having to think about it. So we have a radio signal, or 16 of them. We can talk in both directions. The whole thing is secure. Nobody can listen into it. How do we use that to transmit digital information? Developers of a certain age may find the following sounds nostalgic. That's what data sounds like if you broadcast it over an audio signal. And there is this fascinating little kind of dead end in history. In the early 1980s, in a couple of places around the world, in London, in Germany, I think there was a station in Poland that did this, radio stations broadcast computer games. They would pick a late night slot where there wasn't really anyone listening in to the radio, and the DJ would, play a couple of records, and then he'd tell all the people who were listening in, get your cassette recorder and plug it into the radio and press record, and then for about 20 minutes, they would broadcast a game, a computer game. And the idea was, they broadcast this, you record it onto cassette, and if you had a good, strong signal, and if nothing went wrong, and if you didn't run out of tape, and if there was no interference, you would literally be one of the first people in history to wirelessly download a computer game from what wasn't even the internet. This is late night talk radio. But, this idea of turning data into audio and then turning audio into radio kind of has an upper limit of how much information we can encode into it. What we need to come up with is a much better way of putting digital information into one of these radio signals. And we're going to demonstrate that now, because we, here in this room, are going to be a transmitter. So what I want you to do, all of you, is clap. OK? What we got here, we set up a carrier wave. Now we're going to start encoding some information. So first thing we're going to do, when I shout 1, we're going to clap loud. So ready? 1. Now quiet. 0. 0. 1. 0. All right. This is not frequency. This is amplitude modulation. See if you can guess what's coming next. So the next thing we're going to do, we're going to set up the same carrier wave, okay? Except this time, when I shout 1, we're going to go twice as fast. You ready? 1. 0. 1. 0. This is frequency modulation. We speed up and slow down the signal that we're broadcasting, and that's how we communicate the ones and the zeros. Now, there is another one, and if there's any drummers in the room, you'll get this, and if you're not a drummer, this may kind of mess with your head a little bit. We're going to do the same thing. 4, 3. But now, when I shout 1, we're going to clap off the beat. You ready? 1. 0. 1. 0. And this is called phase modulation. What we do is we take the signal, we don't make it louder, softer, we don't make it faster, slower, we make it earlier and later. So we have these 3 mechanisms now that we can use to push a very simple, basically a number, a digital signal on a carrier wave on a radio. Now, give yourselves a round of applause. This is interference right now. Now, let's visualize what some of this stuff actually looks like. So the simplest possible carrier wave looks like this. It's just this very simple sine wave. And what we're going to do is we're going to take points on that spectrum, on that circle, and we're going to say, OK, if it's here, it's a 0. And then if it's on the other side, that's what we call 180 degrees out of phase. We're going to use that as a 1. And now we can transmit this stream of 1s and 0s. And you can see the way on this, you get the waves in phase, the waves out of phase. In phase, out of phase. Now, there is a limit on a radio signal. It's something called the symbol rate. This is, each of these little vertical slices here is a symbol. And there is a limit to how many symbols we can transmit in a given period of time. So if we want to get more data into it, we either need more power or we need more radio channels. Now, both of those things are expensive. Or we want to come up with a way of putting more information into each of those symbols. So what if, this by the way is binary shift phase keying, 0 and 1. What if we decide we're going to use 4 points around this compass? So we got in phase, we got 180 out of phase, and then we got 2 points in the middle. That gives us 2 bits for each symbol. And we can do the same thing. We can encode a digital stream with that. And you see here the wave starts to get a little bit more complicated. This is what we call quadrature shift phase keying. Let's go again. Let's split it down, break it into 8. Now we can send 3 bits of data for every one of those single points. This, being named by radio engineers, has the incredibly catchy title of Pi/4 quadrature phase shift keying. Brought to you by the people who brought you Microsoft Visual Studio Team System DevOps Enterprise Edition. Let's go even further. What if, as well as changing the phase, we start changing the amplitude as well at the same time? That lets us put 16 points on our symbol generator. So now we're going to get this really complicated looking waveform, but every one of those symbols now can include 4 bits. So we've quadrupled the bandwidth of our system without having to invest in more power or build more transmitters or anything. We're just using the space that we have got more effectively. This is 16 quadrature amplitude modulation. And it gets bigger. There's a thing called 64 QAM, which crashed my JavaScript animator, so I can't show you this one. And there's 256 quadrature amplitude modulation, which is what digital cable TV systems use. And all of these are based on ways of getting more bandwidth, more signal out of the same equipment and the same block of frequencies, because those things are a finite resource. You know, there's a point where we're going to run out, and all we're going to be able to do is use the spectrum we already have more effectively. So all this complexity is going on behind the scenes. And when you get your phone out your pocket, you get this little searching thing, and then you get, bang, 4G, these 4 bars of signal. You're on a 4th generation network. Inside your phone, there are hundreds of amazing components, tiny, tiny little discrete components that are doing all this kind of stuff. And somewhere in your messaging application, there is a chunk of code that looks kind of like this. While true, check for messages. And check for messages here it's an incantation, because underneath that check for messages, there is HTTP, which is the network protocol, and there's TLS, which is the encryption protocol that keeps the HTTP secure. And that's running on top of TCP, which is a guaranteed delivery mechanism. And the amazing thing is that TCP guarantees delivery, and TCP is built on top of IP, which doesn't, which absolutely blows my mind, you know? And then underneath that, we have the physical link layer, which ensures that every packet gets from this piece of equipment to the next one. And underneath that, we've got the 4G and the LTE networks that make it possible. And underneath that, we've got the entire concept of cellular networking. Underneath that, we have radio. It's basically just magic. It's easier to pretend that it's magic. You know, we don't need to understand this stuff to be able to use it to do things. So let's go back to our code. While true, check for messages, and if message count is greater than 0, play the alert sound. So how do we get that sound into a phone? So first of all, phones are digital, computers are digital. We need to take moving air, which is what our ears pick up out of the ether, we need to turn that into a stream of numbers. And if you capture a WAV file or an MP3 file and you zoom right in and you look at it, you'll see that all we're actually doing is we're measuring a whole bunch of points, because you can express audio as a string of numbers. All you're doing is you are just sampling at certain intervals how loud is the sound right now. That's literally all digital audio sampling is. So in this example here, and in most examples, what we're doing, you'll see 2 things written on the back of, say, like a compact disc. You'll see 44.1 kilohertz, 16-bit. Means 44,100 times per second. That's the kilohertz bit. We are saying, how loud is it right now? And we are measuring it with 16 bits of precision. We're using a 16-bit number in that. And that turns this analog waveform that our ears can detect into a stream of numbers. And we have a stream of numbers. Brilliant. We've turned our little alert noise into a string of numbers that we now want to be able to replay on demand, and that means we need to be able to store those numbers somewhere. Except there's a problem, because we haven't invented file systems yet. We haven't invented any way of storing these bits yet. Now, one of the earliest data storage mechanisms, before we had the whole idea of transistors and solid-state memory, you'd take a piece of pipe, piece of glass tube, and you'd fill it up with mercury, because, hey, why not? It's the 1950s, and Uncle Sam is paying. And then you put a loudspeaker at one end of it, and you put a microphone at the other end of it, and you link the one back into the other one. And this is delay line Mercury tube memory. This was a real thing. And it relied on the fact that sound waves in Mercury travel very, very slowly. So you can put a wave into this thing, and it'll take maybe half a second to get to the other end. And when it gets to the other end, you can pick it up with the mic and send it back around and retransmit it. And so by literally setting up a standing wave in a glass column of Mercury, you had a way of remembering a digital signal, 1 or 0, and coming back and reading it again later, which is something we all take for granted. You don't think of having to invent this stuff, but we did. This is the delay memory from the UNIVAC 1. It had 18 memory lines in this unit. Each of them could store 120 bits. UNIVAC 1 had 10 of these units. There is some research that Alan Turing did where he tried to see if you could use gin instead of mercury to make these things work. But unfortunately, history does not record whether that was successful or not. Now, this clearly wasn't going to scale terribly well. Mercury is expensive and poisonous and dangerous and all kinds of horrible. We needed a better system. And somebody came up with a bright idea. What if we put little magnetic particles on something like tape or maybe a spinning disk, and then we can use an electromagnet to zap them and flip them upside down. And then hopefully when we come back to read them later, they'll still be flipped. And we invented originally magnetic tape, and then we invented mechanical hard drives. Now, we got phenomenally good at building mechanical hard drives. What we've got here, each of these platters, this is slowed down 50 times. It's from some guys on YouTube called the Slow-Mo guys. And when we read and write a file from a mechanical disk, what we are doing is we are saying, here are some metal disks that are spinning at 15,000 revolutions per minute. There are a couple of 100 million billion little tiny magnetic particles on this disk. We want you to go to disk number 4, move to exactly this position, wait until the drive head reaches this exact point in its rotation, and then just tell us what the bits are on there. That's the basic principle of magnetic storage, is a stream of magnetic particles, zeros and ones, written onto some physical medium. And then on top of that, if you look at the file allocation tables from the very earliest operating systems, we're talking like CP/M and MS-DOS version 1, it's literally, here's a file name, and it is at this position on the physical disk, and it is this long. That's what the file allocation table is, And we've extended on it since then, because we invented things like symbolic links and directories and folders and all kinds of stuff. But fundamentally, the file allocation table just said, if you want command.com, you go to this location on the physical disk, and you read this many bytes off it, and that's the file that you asked us to store there. Now, around the same time we're inventing disks, we were also inventing RAM, memory. And memory is based on transistors, which are magic. And the way a transistor basically works, it's an electronic switch. It's a little component that you put current into one side and nothing happens. But if you feed in a signal into what's called the base, it effectively opens the gate and it allows current to flow through that device. And you can amplify it in the process as well. And someone came up with the bright idea, if we took one of these transistors and we link its output back into its own base, we effectively then have a device that if you switch it on, it'll stay switched on. And if you switch it off, it'll stay switched off. And then we can use it to store values. We can use it to store a 1 or a 0. Check this out. We don't need any mercury at all. This is really cool. And someone else came along and said, well, there's a slight problem with these, We can use them to build memory banks. If we want to store 8 bits, brilliant. We'll feed all of them into the collectors on all these transistors, and then we'll take that source signal away, and then we can come back later, and we can read out the values in all those chips, and bang, there's our original 8 bits. There's our byte back again. The problem with these is if the power goes out, they wipe. You lose it. Sad face. This is not good. You've lost, I don't know, your homework, your MP3s, whatever you had in there. And somebody came along, and they said, well, I got a good idea. What if we could invent a transistor that remembered whether you'd switched it on or not, even when the power was out? So we could put a signal in, we could switch it on, we could take that away, and it would remember its state. And someone else said, that is actually impossible. Look, we've proved it here. It's totally impossible. And someone else said, yeah, but check this out. We're going to invent a thing called a floating gate. And the floating gate is going to use weird quantum stuff. Does anybody here have small children? Have you ever experienced the phenomenon where your child has a little bit too much sugar, and you turn your back for a few seconds, and when you turn back, your child is in the kitchen eating glue? And the kitchen is locked. There is no way that your kid could have got into the kitchen, But somehow, while you were not observing them, they went into this sort of weird quantum toddler hyper state. And when you turn back again, they were somewhere there's no way they could have been. This is exactly how solid-state memory works. We take a bunch of electrons and do what is really only describable as weird quantum stuff. You put them into a quantum state where their position can't be determined, and you rely on the fact that when you read them back again, some of them will have got into this little tiny device called a floating gate where they will be stuck. And once they're stuck there, we don't know how they got there, they don't know how they got there, but they stay there. And you can come back later and you can read the state of that floating gate and see whether there's electrons trapped in it or not. And in order to erase it, all you do is you push in a massive current through the system, and boom, you get more weird quantum stuff, and the gate's empty, and it gets erased. So we've got this device, this quantum gate, floating gate, which is impossible according to the laws of conventional physics. How much do you think one of these devices would cost? You can get 64 billion of them from Amazon for 30 bucks, you know? Not only are we really good at inventing this stuff, we're really, really good at inventing it and then getting brilliant at manufacturing it and bringing the price of these things down. So literally, when you buy a memory card for your camera or the memory inside your phone, you are talking about billions of these physically impossible quantum tunneling gate devices that we use to store cat pictures and MP3 files and stuff, you know? And as developers, we have all of this amazing magical technology that we can go and play with. And do you know what the magic spell that we have to use to access these billions of magical quantum devices is? It's that. Because we're sitting on top of this amazing pile of abstractions that puts all of this power at our fingertips. So we can call file.read notify.wav, and that will give us back a stream of bits. And then we can turn those bits into a wave, and then we can turn that digital wave into an analog wave, and then we can push that into this tiny little loudspeaker about the size of a human fingernail, and we get an alert noise come out the other side. And we get our phone out, and we look at it, and we go, ah, it's a cat picture, it's Lionel. How did the picture get there? So, now, I'm glad I'm doing this talk here in Australia because it starts with this yellow thing in the corner. Now, over here, you know what that is. When I did this talk in the UK, people were like, please, what is the yellow thing? Light comes out of the sun. You're going to have to trust me on that one. It just does. It comes out of the sun, it travels a couple of 100 million miles across the empty void of space, and it hits Lionel right on his little furry ginger face. And some of it bounces off. The light that bounces off is red and orange and white. And it goes through a lens, and it hits this tiny, tiny little thing inside your phone that's called a photodetector. Now, the brilliant thing about these photodetectors, very, very simple device. You put light in one side, you get electricity comes out the back. The more light you put in, the more electricity comes out. But they can't see colors. They literally only see intensity. So somebody invented this thing, which is an engineer called Bryce Bayer invented this grid of tiny little colored glass crystals that basically allows you to read all the cells behind it, the things that are gray in this diagram. And by working out how much light they're getting directly and how much is coming from the adjoining cells, it can actually work out how much red, how much green, how much blue is hitting every one of the cells in this thing. If you've got a 12 megapixel camera in your phone, which is pretty common these days, you're talking about 12 million of these things inside a tiny, tiny little thing, smaller than your fingernail on the back of your phone. So we take this picture, and what we get out of it is we get a bit map, literally a map of bits, rows and columns. We get 3 of them. We get 1 red, 1 green, 1 blue. We combine the 3 of them. We get out this picture of Lionel. Now, 12 megapixels times, say we're sampling each pixel at 8 bits, so we can go from 0 being completely dark to 255 being bright, saturated. It's going to give us 96,000, so 96 million bits per channel, which means this picture of Lionel is going to come out around about 32 megabytes, uncompressed, yeah? Which doesn't sound like a lot. But the wonderful thing about this tech is that we can use it to send stuff all over the world. So we're all going to get up, we're going to get on a plane, we're going to go here. Anyone know where this is? This is Bratislava, the capital of Slovakia. And the reason why we're going to Bratislava is actually there's two reasons. One of them is that if you are going to Slovakia from Australia, roaming data is very, very expensive. You'll pay $3 for 1 megabyte, and they charge you by the kilobyte, yeah, which is quite a lot. So this picture we got here of Lionel, 32 megs, we're going to pay 96 bucks to look at that cat picture, which I think is a price worth paying, but some of you may not agree. Now, the other reason we're going to Bratislav is Bratislav has the cheapest beer in the European Union. A bottle of local beer there is about €1, which is about $1.60, we convert it. Which means this picture of Lionel is equivalent to this many bottles of Slovakian beer. Now, suddenly we have a reason to see if we can make that picture any smaller, right? Because if we can halve the size, the amount of data we need to transmit that, we get a whole lot of beer to drink while we're sitting there looking at our cat pictures. So how are we going to compress this picture down and get some beer money to spend on our European vacation trip? So we're going to start with the picture. As I said before, when we capture that picture using the camera in your phone, you do it on 3 channels, red, green, and blue. And we have this rule that on each channel, 0 means black, dark, and 255 means as much as you can get. All the red, all the green, all the blue. That is not the only color model that works. It's a color model that works very well for digital cameras. But when it comes to image processing, we're going to use a different system. We're going to split it on 3 different channels called Y, CB, CR. Y stems from the days when this would be X and Y on an old-fashioned graph of time versus intensity. CB, CR stand for chrominance blue and chrominance red. And what we're doing, we're taking every little cell, every pixel in that picture of Lionel. We're saying, OK, channel 1, how bright is it? Channel 2, where is it on a sort of scale of yellowness to blueness? And channel 3, where is it on the scale of redness to greenness? And there's a very, very good reason we're doing this, which is to do with the way the human eye perceives detail and color. We are really, really good at seeing fine detail in black and white. We are not good at seeing detail in color. So we can take this picture of Lionel, we can split it onto these 3 channels, and then we can throw away 75% of the information from the color channels, and we don't notice. Your eye completely ignores this because it's not that good at seeing little details like claws and whiskers and stuff in color anyway. We're relying on the black and white channel for all of that fine detail. So by doing that, we've instantly thrown away about 25–30% of the data that's encoded in that. They normally downsample by a factor of 4 when you're using JPEG compression, which is the algorithm we're talking about here. So we've saved a bunch of data. Now we are going to zoom in really, really tight on this picture, and we're going to cut Lionel into little 8x8 pixel tiles. This is hypothetical, by the way. No cats were harmed in the making of this algorithm. So we've broken this image down. Each of these 3 channels, we got these tiny little 8x8 pixel tiles. And what we are going to do now is we are going to work out, for every one of these, how we can come up with a mathematical recipe to recreate that tile. Now, baked into the JPEG compression standard, there is this thing. This is a discrete cosine. I'll get back to you. I'll put that on Twitter later. I can't remember what it's called. Basically, what we've got here are all of the possible 8x8 tiles that can be expressed as a frequency, basically. And we're going to use these as ingredients in a recipe, and then we're going to play around with that recipe. Now, I understand over here in Oz, you take your burgers quite seriously. So I looked up, this is an Aussie burger with the lot, this is called. And I started looking at this, and I'm thinking, you know, what could we do? How much could we compress this recipe and still get a burger out at the other end of it? So we got this whole list of ingredients here, right? We got buns and mince and cheese and beetroot, pineapple, and all this kind of stuff. What if we left out mayonnaise? Would that still be a burger? I think it probably would. What if we left out ketchup? Is it still a burger? Mustard? Lettuce? Yeah. Now, there's going to come a point. What we're doing here is we are tweaking the threshold of our lossy compression. We're deciding how much information we are comfortable living without. Get rid of the onion. Get rid of the pineapple. Get rid of the beetroot. Too far. OK. So we've hit the threshold there. That's the point at which, if we go any further, we're not going to get a burger at the other end of this recipe, right? But by doing that, we've achieved about 73% data compression on this. And JPEG works exactly the same way. These are our ingredients. Now that white square up in the top left corner, that's your minced beef. That's important. We need a lot of that. But the bottom right corner, these little kind of checkerboard patterns, that's the really kind of fine detail that probably is not that important. So what we're going to do is we're going to analyze each of these little tiles in this picture of Lionel, and we're going to decide we're going to throw away the condiments and the seasoning, and we're just going to try and come up with a really simple recipe for that tile. We analyze each of those tiles, and we come out with a matrix. The matrix tells us how much of each of these ingredients we need to use to get that tile back at the other end. Now, there's a couple of things about this that you'll notice. First of all, the number in the top left in this example is 53. That's really important. That's your minced beef and your patties. You can't do without that. The numbers get smaller, and as we get towards the bottom right-hand corner, we get stuff that wasn't in the burger to start with anyway, like lemonade and stuff. There's no lemonade in a cheeseburger, so that's always going to come out as 0. Now, this is the really clever part. What we're going to do now is we're going to read out this series of numbers, and we're not going to do it in rows and columns. We're going to do it using a pattern called the JPEG zigzag. The reason we do this, one, the most significant numbers, the ones that are really important, they always come out first. So we can make our own decision as to at what point do we stop and move on to the next one. The other thing we can do is we can put a marker in that byte stream which says, okay, you're good. From here on in, the rest of the cell is just 0. Skip ahead to the next tile, skip ahead to the next frame. And that's how JPEG compression works. We throw away the color information, because our eyes can't really see the fine detail anyway. We take what's left. We turn it into tiny slices. We analyze each of those tiny slices. We come up with a mathematical recipe for recreating it. And then we throw away the bits of that recipe that we think we can live without and still get back a passable approximation of what we had. And if you compress a JPEG really heavily and then zoom right into it, you can actually see these individual tiles. And once you know what you're looking for, you'll see some of them are just like a gradient fill. We've thrown away everything except this kind of very gradual color shift from one to the other, because that's a recipe with only one ingredient. It says, just give us gradient for this. That's fine. So we've compressed Lionel very heavily. He didn't really seem to mind. He still looks quite happy. We got this. We saved ourselves a whole load of bandwidth. We can go out and spend the difference on beers. But before we do that, there are rules. This is the internet. Someone sends you a cat picture. You send back lol. Yeah? Now you're thinking, that's text. How hard can text be? And a lot of the ideas we've already talked about in this are about, we take something out of the real world, a photograph. We turn that into data, and at the other end, we want to be able to turn it back into a photograph. We take some music or some audio. We turn it into data. We get to the other end. We want to turn it back into something in the real world. Take a piece of text, turn it into data, turn it back into text. How difficult can this be? And some people are going, yeah, it's easy, it's just plain text. And some people are going, oh, sweet summer child, let me tell you the stories. Does anybody recognize this? Morse code. Anyone know what this says? SOS. Does anyone know what this says? Let me play it to you. SMS. In order to send text as digital information, we need to agree an encoding system between the sender and the recipient. We're going to take something that makes sense to us. We're going to turn it into 010111010. The person on the other end needs to know how to turn those ones and zeros back into something meaningful. Now, one of the earliest text encoding systems that was successful because people could agree on it was Morse code, invented by Samuel Morse. And Morse code's incredibly versatile. You can use zeros and ones instead of dots and dashes. You can use a flashlight. You can use a telegraph key. There's all kinds of ways of sending this code. And it's successful because the people on the other end can recognize what it is, and they can decode it. They can turn it back into text. Now, the problem with Morse code is it's not actually terribly effective. And all the characters in it can be different lengths. So, in the 1960s, the American computer thingy invented ASCII, the American Standard Code for Information Interchange. And ASCII is kind of one of those things we've all taken for granted. It seems kind of weird that someone would sit down in a world where ASCII didn't exist and they would invent it. And when you start digging into it, you actually discover they did some pretty clever stuff when they came up with the way ASCII works. So one of the things we often come across in software is someone says to us, oh, can you give me these records in alphabetical order? And you go, yeah. And then a little bit later in your career, you go, do you want the capital letters mixed in with the lowercase letters or not? Do you want a case-sensitive or a case-insensitive sort? And then even later in your career, you're like, which of the 280 SQL Server code pages would you like me to use for alphabetical order, you know? But one of the clever things about ASCII is they effectively used so ASCII was a 7-bit code, 0 through 127. And the 0 through 31 they reserved for control characters, which literally used to control things. So carriage return line feed. The carriage return would move the carriage and return it back to the other side of the typewriter, and the line feed would feed the next line in the printer. And then for some reason, when we got Mac OS and Linux and Windows, nobody could agree on which one of these actually meant start the next line. But they used 1 bit of 7-bit ASCII. If you want to sort an ASCII text file in alphabetical order and you want it case sensitive, you just sort it numerically. If you want it case insensitive, you just ignore the 6th bit, and you get a case insensitive alphabetical sort out of it. Now, you know, this worked fantastically well for Americans who were reading and writing text written in American English, because the people who invented it had gone, well, what do we need in this code? All right, we'll put all of those in it. That's fine. We have 127 characters. Now, when I was about 10 years old, I moved from Africa to the UK, and I was doing some homework on my 286 PC, and I was writing something which had pound signs in it, the sterling currency symbol. And when I printed my homework, it came out as this. And I had my first experience of character encodings. Because what we had done throughout the 70s and the 80s and the 90s is we'd said, all right, well, American ASCII is 0 through 127, so we'll take the other half, the 128 through 255, and in the UK, we used it to do one thing. And in Western Europe, they used it to do something else. And in places all over the world, they had what they call code pages. These are a different set of standards where you agree on what those extended ASCII characters mean. And the problem with code pages is there was no way within a file of saying what code page you should use for it. You had to know in advance using another channel. Now, anyone tell me what this says? Привет, hi, in Russian. And Russia, of course, does not use any approximation of the Western alphabet. Russian uses the Cyrillic alphabet. So when they started building computers in Russia that were doing text encoding, the International Standards Organization very helpfully said, here you go, Russia, here is a text encoding system that you can use. Now, this is in the days when 7-bit ASCII was so common that a lot of devices could not cope with the 8th bit. They would literally strip it off in transit. You know, there were email systems that would strip the 8th bit off any attached text file. There were network protocols which would drop the 8th bit because they used it for their own purposes. So when somebody wrote the word "привет" in Russian, and they encoded it, and that bit got chopped off by 7-bit encoding devices, and they tried to put it back together at the other end, they would get gibberish. So some Russian scientists went, we don't think the Americans have really appreciated the nuance of our alphabet here. We have a much better idea. So they came up with something called the KOI8, the Kod Ordinat Informatsky encoding. And what they did was they said, instead of using Russian alphabetical order, we're going to encode it based on which English letter is the closest in terms of pronunciation. So you take the word "привет", you run it through this thing, the 8th bit gets chopped off by all these stupid devices, but when you put it back together at the other end, what you get out of it is something which kind of approximates what went into it. They flipped the upper and the lower case on purpose to make it obvious that this thing had been mangled in transmission, but they mangled it in such a way that it was still readable when it came out the other side, which I think is really, really clever. And before we get on to how we solve this problem, there is a really weird historical footnote about all of these different encoding systems. In 1987, Billy Joel played a concert in Leningrad, which is now St. Petersburg, which was released on vinyl and cassette in the Soviet Union. And because it was only released in the Soviet Union, the title of the album is Concert, written on the cover in Russian. And then at some point, someone took the Sony music database and had to start putting it into computer systems. And they looked at this word on the cover of this album and they went, Kohuept? Kohuept. And if you go on iTunes today and search for Kohuept Live in Leningrad, it's a real album, it's on Spotify, it's on iTunes, it's on Google Play. all because of this little encoding glitch from the 1980s that everyone thought we had solved, because no one has come up with a way of kind of retrospectively going in and fixing this stuff. And even if they could, if they gave it the right name, you wouldn't be able to search for it, because you don't have those keys on your keyboard. So, historical footnotes aside, enter the Unicode consortium, who were like, we should sort this whole messy business with the code pages and stuff out once and for all. Let's actually fix this problem. And what the Unicode consortium did, they actually only solved half the problem. Because what they said they were going to do, we want to give a unique code point to every character in every alphabet that is or has ever been used by humans. So they came up with a couple of ideas. First of all, they're like, from 0 to 127, we'll do the same as ASCII. And I'll talk in a second about why this was a brilliant, brilliant solution. And then they just went, well, we've got all the space to play with. We've got a theoretically unlimited number of code points. Let's just start dropping alphabets into them and giving them all code points. So we have distinct code points for English and Russian and Greek and playing card characters. We even, if you really, really want to compress data and send stuff around the world quickly, the best thing you can possibly do is to agree in advance a code point for the thing you want to send. Does anyone know what this is? I'll be amazed if you do. This is domestic cat facing left. This is the ultra-compressed version of Lionel. It's one Unicode code point. Now, the Unicode consortium said, here you go, we've given numbers to all the letters and all the alphabets. It's your problem now, engineers, you go and fix the rest. And everyone went, okay, how hard can that be? So we've got, let's say we're going to use 4 bytes. So we're going to use 32 bits of space to encode all of the characters in our text file. And the first character you see is A. And you go, well, obviously, A, the ASCII code for that's 65, and Unicode uses the same as ASCII for that. So A will be this. And then the old dude in the back with the beard who remembers how C and C++ work goes, son, I see a problem with your text file here, because there's a lot of software out there which cannot cope with a byte that is all zeros. Does anyone want to tell me why? It's a null termination character in C and in C++ and in languages influenced by them in the way they handle strings. And so an awful lot of the utilities and applications that exist on most modern command line systems just are not designed to cope with a text file, which has a string of 8 zeros in it anywhere. So they had a bit of a think, and they came up with what I think is a really, really clever solution to it. They came up with UTF-8 encoding. Now, the brilliant thing about UTF-8, UTF-8 files and ASCII files are interchangeable, because every ASCII file that only uses 7 bits of ASCII is also a completely valid UTF-8 file, and it's exactly the same. So all the files that already exist, we can keep using them. They then come up with the idea, okay, so we've got the 8th bit, the bit that kept throwing people off the mark back in the day. Let's use that as an indicator that this byte is part of a UTF-8 byte sequence. And they said, if it starts with a 1, 1, that means this is the beginning of a multi-byte string. And if it starts with a 1, 0, it means it's a continuation character. Go back to the previous one, that's the beginning, and then read forwards from there. And the brilliant thing about this, and then the rest of it, the bits which are red X's in here, that is the number. That is the numeric value that you're working with. And this expands. If you see 1, 1, it means this is 2 bytes long. If you see 1, 1, 1, it means this is the start of a 3-byte sequence. If you see 1, 1, 1, 1, it means this is the start of a 4-byte sequence. This gives us enough address space to go up to theoretically 8 bytes, which is 256 bits, which is a phenomenal amount of storage. That's enough for all the human alphabets, all the historical human alphabets, all the fictional human alphabets, all the alphabets we're going to have to deal with when we make contact with Alpha Centauri and start trying to send email to other star systems. And we've still got enough space left over to invent emoji, and cats, and hearts, and smiling faces, and bees, and all these little random characters that people can now use to send messages to each other around the world. And the fantastic thing about all of this complexity, all of these solutions, all this technology, is we as software developers, we can use it without having to understand all the details of how it works. There was this great XKCD strip a couple of months back, which opens with someone saying, you know, I had this app and I had a calendar web page, and I wanted to show them side by side, but the operating system didn't have split screen support. So I decided to build my own app. And then I realized it would be easier to get 2 small phones on eBay and glue them together. And on that day, I achieved software enlightenment. And then the last frame, the guy in the hat said, but you never learned to write software. And they said, no, I just learned how to glue together stuff that I don't understand. Fair enough. Now, that's important, because that's what we do. That's how we do it. That's what all of us are doing now when we build software applications. There's nobody left in the world who wants the kind of applications that are built by someone who understands the registers and the processes. There was a day, probably in the 1980s, when you could literally put a computer together by soldering components and then write games on it that were so good your friends would come over and want to play on them. But, you know, the stakes are so much higher. We can do so much more now. The people who invented JPEG compression and the people who invented 4G cellular networking, they didn't do it so that you could send cat pictures to someone on a train. They did it because they were like, if we can solve this problem and we can put the solution out there, other people will use it to create cool things. Let's build it and put it out in the world and see what they can do. And the reason why, you know, we do this, the reason this stuff works, is most of the time, these solutions work really, really well. They work so well, we take them for granted. They're ubiquitous. And it's only when you get your phone out and you can't get any signal that you even stop to think for maybe a fraction of a second, hang on, maybe this was actually, maybe there's quite a lot going on here that normally we take for granted. Over the next 3 days, you're going to have the chance to talk to each other, to talk to the speakers, to talk to the sponsors, talk to the organizers. All the people who are here because we want to build cool stuff. We want to glue together things that maybe we understand, maybe we don't understand. And we want to build interesting applications and create great user experiences and solve problems, do all this kind of stuff. And one of the reasons that these conferences like NDC are so fantastic is because you can have those kind of conversations face to face. Now, I want to give you one tip. How many of you here is your first time at, is anyone here your first time at any conference ever? Okay, that's cool, we got a couple. How many is your first time here at NDC in Sydney? All right, awesome. Very glad you're all here. There is a thing, Eric Holscher's Pac-Man rule. This guy, Eric Holscher, came up with this. I think this is a brilliant rule. It's about a way of being friendly and a way of encouraging conversations. If you find yourself, you know, out there or maybe in the bar at the party and there's a couple of you stood around in a circle, there is this very easy human thing. If you arrive somewhere at 10 o'clock in the morning, you assume the people who are there at 9 o'clock are all lifelong friends and they know each other and you're a stranger. And so you feel like you're interjecting. And it feels rude kind of going up to people and going, hey, can I join your conversation? So there's a very easy rule. If you find you're in a circle and you're talking about Angular or React or progressive algorithms or whatever, somebody comes up, they won't be able to join your group. So remember Pac-Man. If you're standing in a circle, leave a space. It's really easy. And then somebody else can come up and they can join in. And as soon as they join, of course, you move out. You make another gap. Just this one little simple thing can make the whole experience of meeting people, exchanging ideas, you know, swapping war stories about that horrible thing that you all had with Entity Framework, all that stuff go so, so much easier. So now that we've dug into the technology, I just want you to watch this clip one more time and think about what's really going on here now. Thank you very much.
Thank you, Dylan. Once again, give it up for Dylan Beattie, everyone.
Thank you.
So what do you give a guy with 100 hats? Another hat?
Another hat. That's beautiful.
Brilliant. So yeah, this is the third NDC Sydney we're doing. But there's actually our fourth conference here in Australia. We've done a security conference on the Gold Coast before. So who's been to all 4 conferences in Australia from NDC? Oh, there's a hand. What's your name, sir?
That's Troy Hunt.
That's Troy Hunt? Then you get to speak next.
Have you met him?
In this room. That's Troy Hunt after this. Thank you all for coming, guys. Have a good conference, and we'll see you around.
And all the people who bet me a beer I couldn't talk about one cat picture for an hour, I'll be in the bar. Thanks a lot. Have a great conference.